and welcome to Aerotech's Automation1 Motion Control Platform Educational Series. Aerotech is a company that solves your toughest precision motion and automation challenges. Automation1 is a motion control platform consisting of software-based controls and development tools, PC and drive-based control hardware, and hardware-based drives for servo motors and other devices. In this video, you'll discover what the command shaping feature of the Dynamic Controls Toolbox is and how this can be used to improve your system's performance. My name is Alex, and I'm a control systems specialist for Aerotech. The Dynamics Controls Toolbox is a series of optional purchasable controller features that supply algorithms and tools that can improve the motion performance of your stages. You will often hear these features referred to as DCT or the DCT tools. There are a few different tools within the Dynamics Controls Toolbox. In this video, we will touch on just one, and that will be the Command Shaping Toolkit. Command shaping is the ability for Aerotech to remove move-induced vibrations that can occur in lightly damped mechanical structures. It does this by filtering the position command of an axis so that the move does not excite vibrations that could occur due to the mechanical system. This is sometimes referred to as the diving board effect, where when you jump off of a diving board, the diving board continues to vibrate until it comes to rest. This is similar to the kinds of things that command shaping counteracts. Now, command shaping is what's called a feed-forward technique, meaning it takes place only on the servo system's inputs, like position command, and not position feedback. This means that command shaping can be used to reduce vibrations at a work point, even if the vibrations are not being seen by the controller. Some common application uses of command shaping include electronics manufacturing, semiconductors, or even some DNA sequencing applications. Anywhere where there is a step and settle or pick and place type of motion that can induce these kinds of vibrations. This is where command shaping really shines, with its ability to reduce the vibrations and settling time that could occur as a result of rapid start and stop motion. A few other things that we can note about command shaping. In Automation1, command shaping can be applied at 2 frequencies per axis. The other thing to keep in mind is that command shaping does have a minimum frequency at which it can actually be applied. In Automation1, this minimum frequency is 1 Hz. Take this example. In this, we performed a step and settle move using a linear stage. During the settle portion, our system saw a very long settle time due to the vibrations from the mechanical setup. Now, just to re-emphasize, these vibrations are not due to poor servo tuning. Rather, this is just because there is nothing to dampen the stage response, like a heavy payload, to reduce the overcompensation by the controller during the quick step and settle move. That is not to say that some clever servo tuning certainly couldn't help, though. In blue, we can see the original baseline response from the move. We can see that it takes roughly 600 milliseconds after the move to get within a plus or minus 1 micron threshold. In red, we can see the result from command shaping the response. Here, it is clear to see that our settling time has greatly improved. We are now able to get within the targeted settling time, like plus or minus 1 micron, for example, much faster by counteracting these oscillations. Like everything, though, command shaping comes with its own sets of pros and cons. On one hand, command shaping has the ability to be extremely effective in reducing these movement-induced vibrations. Additionally, because this is just being implemented as a feed-forward input, the overall stability of your servo system is unaffected. This means that you may not necessarily need to tune a complicated system for one specific move. While tuning a system for a specific move set is a good thing for stability, it can be hard to tune both that for a specific move and do this for every location on something like an XY plane. Because of how command shaping is implemented, it can be used to more universally affect these kinds of vibrations that you see in the step and settle movements, regardless of the location on the XY plane. Finally, command shaping, because it is an addition to the system, means that it can work with other techniques within the Dynamics Controls Toolbox and tuning in general. This means, again, that command shaping tools are not going to affect the overall stability of your servo systems and can be used in turn with other types of advanced algorithms that the Dynamics Controls Toolbox offers. Now, however, on the other hand, there are some cons of using command shaping. For one, command shaping can only be used for movement-induced vibrations, so this is not a replacement for poor servo tuning or highly unstable systems. Command shaping is also not a be-all end-all universal solution for movement-induced vibrations. Command shaping still needs to be configured for a specific frequency, otherwise it will be ineffective. Finally, command shaping, because of how it is implemented, your velocity command times are lengthened due to the filtering that Aerotech does to the inputted frequency. We're going to show you this and see this in a demonstration in our example later. So now that we know what it does, how do you use it? Well, to use command shaping, you first must know 2 things. 1, the frequency of the oscillation you're trying to dampen, and 2, the dampening ratio for that oscillation. Obtaining the frequency is the easy part. For this, you simply need to take a plot and measure what the period of the vibration is. To calculate the proper dampening ratio, however, we will need to use the following equation. When we go through an example of configuring command shaping, we will show you how we can calculate using these required variables as shown in the equation. However, for the layman, the good old guess and check method might just be as effective. Think of the dampening ratio as effectively how much oomph you need to dampen the vibration. Your typical dampening ratio will usually be between 0.01 and 2, however this is not always the case, and for best results we will still want to go through the equation method. But before we get to our example, let's review the parameters that we will be using. First, when you are looking at the command shaping parameters, make sure that you are under the View Shapers view. If you are not in the View Shapers view, you will see all of the list of coefficients used in the algorithms. The View Shapers view will be much more easier to work with. Within the proper view, you will see 7 parameters. This includes the enable or disable parameter, and both sets of the command shaping parameters to allow you to apply it twice per axis. The command shaper setup parameter will be used for enabling or disabling command shaping. The command shaper dampening parameter is where you will enter your calculated or guessed dampening ratio. And the command shaper frequency parameter is where you will enter the frequency of the vibration or oscillation that you wish to counteract. Finally, the command shaper type parameter will specify which type of command shaping that you plan on using. This gives you the option of standard versus extended. The difference here is that the extended option will improve the robustness of the command shaping, but at the cost of longer commanded move times. In other words, the time to complete the velocity command will take longer with the extended option. We will attempt to demonstrate this in our example as well. Alright, now that we've gone through that, let's go through a quick example to show you how to measure and configure command shaping. For our example, we'll be using one of Airtek's Automation1 demonstration kits. To give you an example of what this looks like, we'll include an image for reference. Essentially, this will include a small weight mounted on top of a small linear motor-driven stage, where the weight's going to be fairly high up above the tabletop to exaggerate the vibrations that we expect to see. Alright, so what we first want to do with command shaping is actually show you where the command shaping parameters are located. So those are going to be here under configuration, and if we scroll down to optimization, we should find them here in command shaping. So these are going to be your setup, your type, and your dampening ratio, as well as your frequency. Now, aside from us going through these, what you might need to do on your demo kit is to tweak some of the parameters a little bit because of the size of the stage we're moving and the mass that we want to try and excite. You kind of have to get a little bit clever with some of the parameter changes. So we're going to be executing very fast, very high acceleration moves. And to be able to do that, I had to both increase the position error threshold to 1, as well as increase the max speed clamp to 500. I also have my in position distance set to 0.5 microns. So 0.5 microns is going to be considered when the stage is at rest or in position. For our example, I also have a program here that's going to enable and home, set a very high acceleration rate for our move, and then both make a very fast move as well as collect the data at the same time. Now, for the kind of plot that you're going to want to configure, there's a couple signals that we want to add to the defaults. So if we go ahead and quickly restore the defaults to show you what you're starting from, you'll want to set the time to collect to large enough that you can collect a full move. But by default, we're collecting x-axis position error, velocity command, and current feedback signals. Those are going to be fine for what we need to do. Really specifically, though, we just want to look at velocity command and position error. The other signal we want to collect is going to be the drive status. Specifically, we want the in position bit. And that's just going to allow us to differentiate how quick our stage goes from finishing a move to finally settling to being in position. All right, so now that we have all that set up, let's go ahead and make our move and see what our baseline plot is going to be. So this right here is just going to run through our quick program here and show us what the baseline of our move is going to be. And from that, we can calculate the settling time, our frequency, and the dampening ratio for our command shaping tools. So here we could see our move. We could see from when we stopped right here, velocity hits 0, to when the stage actually hits its in position threshold. So here's when it's finally considered sitting still. That takes about 0.124, 125 seconds. So a little over a tenth of a second, and we finally come to rest. But here we can see those exaggerated oscillations and frequencies that we're going to try and shape out. Now, the first thing we need to do for this is actually figure out what those frequencies are. And you can do that a couple of different ways. You can, one, just try and use the cursors and estimate using a period, one single period, so peak and peak, to figure out what that frequency actually is. And that is around 40 hertz. So that's probably pretty darn close to what it is. Depending on what the resolution of your plot is, what you could also do is just compute an FFT. So for doing that, we can be a little more accurate. We can put our cursor here where the velocity command hits 0, and then finally somewhere where we're considered at rest. And when we can compute an FFT, we can actually use the data between the cursors option. So that'll only compute the FFT of what's in between our cursors here, which should theoretically just be this oscillation. So we'll do that for the position command, or the position error. And we could see more specifically, okay, so it is right at 40 hertz like we originally thought. So we'll end up using 40 hertz for our example. That's going to be the frequency that we're going to try and shape. The other thing that we need to try and do is figure out what gain, what command shaping damping gain we want to try and use. Like I said, we can use a guess and check method, or we can go through the equation and try and calculate this manually. So for the equation, it actually asks you for a couple different variables. It asks you for the number of periods, it asks you for the first period's position error, and then the final period's position error. So we'll just first figure out how many periods we actually have for this move. And to do that, we could just put our cursors at the tops of each of our peaks and say, okay, that's 1 period, 2 period, and then it looks like there's another one around here, so I'd say about 3 periods that we can actually measure. Now, as far as the actual errors of those, we can just put our cursors at the first one and the last one, and look down at our cursor display and say, okay, for the first one, we are about 0.033 and 0.0030. Those are going to be our x0 and then our xn. So if you were to actually go ahead and plug these into the equation, you should actually come out to something around 0.11. I went through and did this before preemptively, and that's what it does come out to. Around 0.11 would be our ideal damping gain. So that's what we're going to end up using for our example. So let's go ahead and go back into our configuration and input some of those values. Make sure we have the x-axis selected. We'll first show you what the standard is, and then we'll show you how extended kind of changes the response a little bit more. So there's our 0.11 and our 40 hertz. We will enable, save and reset. And let's rerun our program and see how well it improved the response. So here we can see this does look a little bit different. Our velocity command has changed, but more specifically, we can see that the response after the step move is much better. It is getting to in position much quicker than it was before. And we can actually overlap some plots just to show you this a little bit better. So here is our move. We could see in the orange, this is our baseline plot, and then we could see in the blue what our after command shaping response looks like. But through this, we can see kind of the effects that command shaping has on the actual move itself. So we could see how the velocity command is shifted. It is stretched. It's a little bit different. It's not exactly what we told it to be because we are doing a little bit of filtering on the front end. But we can see that, as opposed to previously where we were seeing about 0.124 seconds for our settling time, if we were to zoom in here and do that measurement again. Let's see, so the velocity finally hits 0, commanded velocity around right here. So this is when our velocity for command hits 0. This is when it's supposed to say, okay, we are now at rest. So as opposed to the 0.125 that we saw previously, here we're seeing about 0.04. So that is a pretty massive difference in terms of how quickly we're able to come to a settling portion or come to a settle from our move. And that's just a result of the oscillation of the counterweight that we have mounted. So now let's go ahead and show you what the extended option does. So the extended option, like we said, is just going to make the system a little more robust in how it does the filtering, but at the cost of a longer velocity command. All right, so let's go ahead and run and see what that plot looks like. So it doesn't look like much here, but let's actually go ahead and overlap this plot with our previous command shaping plot just to show you what it looks like. So here you can see our settling time is a little more, it's about the same. We could see some drops here and there, but it does make the settle a little more robust. We can see the error is a little smaller if we zoomed in. It's a little more constant with what it's trying to do. But we can see just how much more the extended option exaggerates that extending of the velocity command. So this is already on top of what's going on with the standard command shaping tool. But overall, this should give you a good idea of how to configure the command shaping using the parameters, as well as measuring what the frequencies and calculating what the command shaping damping gain should be, as well as just using the cursors to measure and actually see what our step and settle time improvement is. That concludes this motion control platform educational video. Thank you for watching. I hope you enjoyed learning about what command shaping is and how it functions.